All right, up and running. Lesson 10. Going to be slightly different approach here. I'm going to turn that way a little more. I'm going to ask you some questions. I'm giving you the trio of big F, little f, and f prime. And right in the middle, little f, square root of x. And I want to ask you some questions about big F. When is it concave down? All right, you stop the video, pause for a minute, and see if you can answer that. And I'm just going to keep going. All right, so square root of x, first thing I want is to look at the graph. And first derivative, when dealing with concavity, is all about whether this is increasing or decreasing. And I can see it's always increasing, so big F is always concave up. It's never concave down. What else can I say about big F from this graph? What other characteristic of this graph do I see? I see positive numbers. And each positive is a little bigger than the last. All right, and what do those positive numbers represent? Slopes of tangents. So this slope right here, maybe that's going up at 1 to 1. And then that slope is a value of 2, so I'm going up at 2 to 1. Maybe this is a value of 3, I'm going up at 3 to 1, something like that. And I can see the concave up and always increasing. And I guess the next question is, what am I looking at? What is big F? Can you tell me what to write to represent big F? You pause on the video. And hoping integration came to mind. Changing square root of x to x to the 1/2 dx. And we're going to be looking at that conceptually. See what that means to you. All right, we've got to develop a meaning for it. All right, and so this is an indefinite integral, so I got to have a plus c over here. And the mechanics of that are x to the 1/2 plus 1 divided by 1/2 plus 1, which is x to the 3/2 divided by 3/2 is multiplication by 2/3. And this one should look pretty familiar. We've been working with that in past lesson sets. So that's what f was. And down here I asked the question, well, if x was 25, and this function comes out as a 3, can you tell me what c is? So that's number 6 down here. We'll get rid of that right now. So we'll draw 25 in. Square root of 25 is 5. Times to the third power is 125. 125 divided by 3 was not the most friendly. So it's 250 divided by 3. And I got to get 3 out of this, so I need this to equal 9 over 3. So I guess I'm looking at minus 241 over 3. Yeah, I hope I didn't make a careless error there. Yeah. But we'll go back to just leaving it as a c for now, because I just wanted you to solve a little differential equation there. But let's just leave it there. How about the derivative of f prime? Can you tell me what the derivative of f prime is? Well, again, if we have x to the 1/2, then we have 1/2 x to the minus 1/2. And do you remember how I wanted you to write that? Pause the video. Yeah, I hope you're saying 1 over 2 times the square root of x. Much easier to work with that. All right. How about the area under this curve from 4 to 9? Well, from 4 to 9, we've got something on the left called an altitude of 3. Oh, no, 2. 4 was over here, right? The x equals 4 here. And over here, we have a height of 3, where x equals 9. And we're going to find the area, the actual area. But before we do, let's estimate it. Let's estimate this area. All right, with one big rectangle, a left-hand rectangle. There we go. There's the left-hand rectangle. It's a height of 2, a width of 5. That's 10 units of area. The actual area is a whole lot bigger, but this is error. All right. But to get a feel for area under a curve, rectangles help. So why don't we do a Riemann sum is what it's called. Let's write 3 right-hand rectangles, and we'll do the JTC. Do you remember what JTC stands for in these videos? We're just going to write the calculation. All right, so we're going to do 3 rectangles. There's the first left-hand rectangle, There's the second left-hand rectangle, and there's the third. Okay, so I've got to define those. So I know the whole width is 5, so that's 5/3 for a width. And 4 could have been written as 12/3. 12 and 5 is 17/3. Another 5 makes it 22/3. And now I'm ready to write just the calculation. So the width, 5/3. This is starting to flow a little more easily than several lesson sets ago. Now the repetition's starting to kick in. So we got 5/3 times the first altitude, which is 2. The second altitude is the square root of, remember this is a square root function. If I take that x and I take the square root of it, 17/3, and I need the square root of 22/3. And if I had a calculator, this would tell me what these three areas add up to, and that's getting closer to the actual area. Now let's do 3 trapezoids. 3 trapezoids means I connect, kind of looks like a trapezoid right now, that, and that, and it's going to slightly, only slightly underestimate this curve. But what do we need? Oh, there we go, those are our 3 trapezoids. Our widths get divided by 2, so this becomes 5/6. I need the first altitude, which is 2, but this gets used twice for the trapezoid on the left and the right, so I got to put a 2 in front of that. And this one gets used twice, so I got to put a 2 in front of that. And the last altitude gets used. And the last altitude is the square root of 9, which is 3. And now I have a trapezoidal approximation, which is even better than the 3 left-hand rectangles. All right, now you find the actual area. We've already done this problem a couple of times in previous lesson sets. Let's see if you can get those memory banks working for yourself. So we're integrating, and I'll write x to the 1/2 instead of that, from 4 to 9, dx. And I think we've seen this enough to go right to the chase. And I think I put 9 in enough to even think, without thinking, that's 18. And this is 16/3. So there's our 54/3 minus 16/3, which is 38/3. And that's the actual area, the exact area under the curve, using the notion of limits, eliminating more error with more and more rectangles, an infinite number of rectangles. Okay, so did I miss any questions from this? Well, let's give you the square root of the sine of 5x. What's the derivative of this? Well, the only thing that changes over here is what's inside is the sine of 5x. But I also need the chain rule. The derivative of sine of 5x is 5 cosine 5x. And so we just got a little practice with taking that derivative with respect to the chain rule. That doesn't hurt. Let's get a few more problems to be done. I wrote out a few more of typical problems. Can you maybe do that integration? We just started with it. You pause the video and try. Before you pause, see if you remember some. It's nice if you can just write the answer. That answer over here is, you pause the video and go after it, I'll just write it. So I got 3, I think it's 2e to the x cubed. 2e to the x to the 4. Over 4. 3x squared. That's 2. E to the x. So it's 3x squared. I'm taking a derivative in my mind right now, which is exactly wrong. So, all right. I thought I was going to be able to do that. I think it's 2e to the x cubed. But I think I'm not feeling confident at all, plus c. I'm not feeling confident at all, which means I've got to go back and refresh my memory and actually do the u substitution. So we'll let u equal e to the x cubed, and so therefore du is 3x squared dx. And therefore, we have our substitution of du over 3x squared equals dx. You know, I've done this for a long time, but I totally am losing my memory, so got to reconnect with it. So now I can replace dx with du over 3x squared. Okay, it looks like I got to get rid of the chain rule here. Got to divide by 3x squared somehow. So maybe that's what's going on over here, but let's find out. Let's find out. So that becomes a 2. That becomes a u. No, that's all it is taking the 2 outside. That's all it is. And that 2e to the u is 2e to the u. So I was correct. Yeah, no, that's what got rid of that. Had a moment there. And so now all we have to do is replace u with x cubed. But this is what you have to do. You have to explore. And when you do something stupid, you got to correct it. Learn from it. All right, so it's been a while since I've done the integration with u substitution, and it was like floating around in there. And that'll help me the next time I do it. Hopefully do it a little quicker and easier and better. That's the nature of the beast. All right, so if I took this derivative, it is itself, times the derivative of 3x squared, which is 3x squared, and that's where our 6x squared came from, e to the x cubed. Okay, so it doesn't hurt to see that. We'll change the limits of integration here soon. There's another topic that branches off of that, but once we get good at that, then the other will be a little easier to see. All right, do you remember the derivative of secant? It is secant x. In this case, x, what's inside is a function, so with respect to where you are on the curve, tangent with respect to where you are on the curve, if I said at x equals 1, you're not at the secant of 1, you're not in Kansas anymore. You're at the secant of 3. And that's where we got to figure out how things are changing with the secant function. And the derivative of 3x times 3. And there you go, a little practice with remembering the derivative of secant and practicing the chain. Looking at a couple of quick limits. Hope you did enough of these rational function limits in your Algebra 1, Algebra 2 trig classes. So just looking at it, when we go to infinity, we're going to go with 5. Okay, when we put really, really big numbers in, squaring gets you 6 decimal places, whereas multiplying something with 3 decimal places gets you 3 decimal places in the linear term. So these things overtake those other terms as we get to throwing in a million, a billion, a trillion, quadrillion, zillion, whatever. 5x squared over x squared goes to 5. Now when we're looking at local behavior, then we're looking at the last two numbers right there. It's just the reverse. When you square 0.0001, you get a smaller number than what you started with. Right? But if you multiply that number by 5, you got a bigger number than you started with. So these are the terms when we go to 0. I think I wrote that. So when we go to 0, we're looking in the other direction, and I can immediately see that when I put negative 0.001 in here, it goes into 7 awful lot of times negatively. And when I put positive 0.001 times 3, going to 7 a lot of positive times. So this does not exist. Now remember what the denominator is. The denominator is x times x plus 3. So we have an asymptote at x equals 0. And if this is going to 5 on the right, positive infinity on the left, that's a height of 5. It also goes to a height of 5 over here. But it's undefined at 0, so voomp, right through. And we can see that there's another asymptote over here actually. So I'm not quite sure. At negative 3 there's an asymptote, so it probably looks something like that over here. Could get into it more, but no need to. We could get a sense from just plugging in some numbers like negative 0.001 and positive 0.001, what's going on. Alright, so I wanted to introduce one other concept here today. There's this thing called the mean value theorem for integrals. So let's just say we have an exponential function, and I want to know its average value from 0 to some number out here. Let's call it 5. What's the average value? Well, it turns out if you draw a height, you kind of get those errors. Well, it's not error on the right, it is part of the actual area. but offset by the error over here. And that becomes our, what we call our average value, our average altitude. All right? So let's just say that we had this function f of x. All right? And first off, it creates an area, yes? It creates an area. And how do you find height? Well, height times width equals area. Looks like if we divided the area by the width, we're going to get the height. And so if I wanted the average value of x squared from 0 to 10, say, I got a parabola. We got 10 getting us 100, 0 getting 0. We got this area. What's the average height? Well, I think I'm right about here. I think that area 1 offsets area 2. And so I think that this rectangle is a good picture for the actual area. So I've got to go from 0 to 10, which is 10 minus 0. That's the width. I have to find the area under the curve. That's integrating x squared from 0 to 10. And if I do that out, I get x to the 3 over 3 divided by, dropping a 10 in gets me 1,000 divided by 3, and dividing that by 10 means I'm dividing this by 30. And we can cancel one of the zeros. And so it looks like I've got a height of about 33 1/3. Is that right? And that's what this altitude would be. That would be up 30, a little more than 33 units. 33 1/3. And that's the average value of this function from 0 to 10. Okay, I hadn't done that in a while. Do you recognize this limit over here? Well, we can actually get the answer to that using algebra. So let's do that out. Kind of proves why the square root of x, what that is for a derivative. But let's do this. Let's take square root of x minus 2. And you're used to, all right, it should be outside the radical sign. You're used to doing conjugates in the denominator, but let's do one in the numerator. See where it goes. And let's do the same thing in the denominator. Okay, so I haven't changed anything. I'm just multiplying by the number 1. In the numerator, I get x minus 4. Well, that's kind of nice because I got x minus 4 in the denominator. So I guess square root of x minus 2 means that I can reduce this to 1 over the square root of x minus 2. I think I can drop a 4 in there. And let's see now, it's plus 2. I know I did something stupid there. So I think I can drop a 4 in there now, and I get 1/4. However, if you get really familiar with how limits create derivatives, you might have recognized that you were looking at the square root function. And if you put a 4 in, you get a 2, which means that this was x1 and this was y1. And as x goes to 4, we've talked about from 10 to 9 to 8 to 4.01 to some x value that's really close to 4, creating dx. All right, and then whatever that value is, I'm taking its square root. Can you see in that calculation y2 minus y1 over x2 minus x1 at an instant? Oh, yeah, whoa. So, we're looking at the square root of x. We'll call that f equals the square root of x. We know f prime is 1 over 2 root x, and I drop in a 4, and I get 1/4. So I just found that the square root of x at 4 is going up at a 1 to 4 ratio. So at 4, I have a y value of 2, and I'm going up at 1 to 4. And we might as well look at the inverse of that. At 2, I get an output of 4, and the square root, x squared, 2x times 2, so I get a 4 to 1 ratio. Must be a coincidence. Alright, so now let's bring this over a little bit. Can you take the derivative of secant squared of 5x? Well, secant squared comes from, pause the video, I hope you know, tangent of 5x. And the derivative of 5x is times 5. So that's, oh, I wanted big F. Ah, why did I say this? Because that would have been a whole different, lapse there. I forgot what I was looking for. Big F. Yeah, that's the tangent. That's 5 times the tangent of 5x. Woo! I was looking at this going, wait a minute, little f prime. Boy, that's a big time chain rule. I got to do 2 secant, bring it down 1 with respect to 5x, times the derivative of secant, which is secant of 5x times tangent of 5x, times 5. That gets tricky when I am talking to you, thinking about the next problem, and I forgot which one I just asked you. All right, yeah, getting harder for me to do that. So I've got f prime is sine of 2x times secant x, and I guess we're going to look for f double prime. Just get a little practice here taking that derivative. So go for it. Hope you're seeing the product rule. Derivative of sine is cosine of 2x, and I need a times 2 there to take that derivative. I'll leave this one alone, secant of x. Gets a bad looking c. And then I have to do what? I have to leave the first one alone, but I have to take the derivative of secant x, which is, we just did it, secant x tangent x, and leave the first one alone, sine of 2x. And you go to the playlist and look at why the product rule works. Now we got the quotient rule. Okay, pause the video, see if you can do low d high minus high d low over low low. Low, so I'm looking at big F, so here I'm looking at little f. Let's do it here though. Make sure you can see this. Low, cosine of 4x. D high, I like doing this again because I forgot to write the element of 3 one time, and this reminds me of that terrible moment. Low d high minus high. Low d high minus high d low. Low d high minus high minus high 3. Yeah, you can tell I'm losing my train of thought. Minus high, excuse me. D low is negative sine of 4x times 4, so minus 4 sine 4x. Yeah, let's make sure I've got that in the numerator. Low, d high, high, d low. Okay, I feel good about that. Over low, low. So we got to square the denominator. And there's your quotient rule. Now we'll do one with implicit differentiation, just for practice. Let's see now. I haven't got it down to just looking at it and writing an answer, so I want to practice that. Put myself under a little pressure. So this is going to go to the other side as minus 10x. This is going to be going to the other side as minus 3y squared. Feeling good so far. I'm going to divide by 6xy. I'm going to divide by 6xy. And then I'm going to divide by minus 12y squared. All right, let's see if I'm getting any better. So this, taking the long route, is 10x dx plus 3 dx y squared plus 6xy dy minus 12y squared dy equals 0. When I divide by dx, that will cancel, but I will get y prime over here. So this is what you will be doing eventually, not writing out that line of work, but hopefully going to this one. By the end of the term, hopefully just writing your answers if we get enough practice. So what happens here now? I've got 10, cleaning it up, plus 3y squared plus 6xy minus 12y squared. Taking a little more time here because I am making a lot of careless errors when I rush. And I like to rush because I like a lot of volume every day. And then if I have to, actually take some time with something, okay, well, get the pencil and paper out and hopefully see that 10x. So I forgot to write an x here. Here I said I was taking time and I forgot to even copy it properly. So I hope we can see how this is going to go to the other side, which validates that. 3y squared is going to go to the other side. Yep, that validates that. I've got a 6xy y prime here. I forgot to write my y primes. What happened to them? I don't know. I got y prime. Well, I guess I did it here. And then this one is also a y prime. And so I can take y prime and I can factor it out. 6xy plus 12y squared. And that's multiplication on the left. What's it going to be on the right? Was that a positive? This was a negative. Okay, so you can tell I'm thinking about where I'm going and not really looking at the numbers enough. But yeah, so this is okay. So starting to get to the point where I can trust that, but not yet. Not yet. I'm still making little forgetful glitches. But again, if I was going to do it for a key on an exam, well, yeah, I'm going to write it out. All right. In the long run, save some errors. All right, so I guess that's that, and then we'll pick up again with 11 and 12. Maybe I can start just putting 30 problems on the board and doing them one at a time over here, and talk a little less. But I was going to talk about f of x dx, what that means to you. Okay, to me it means, and I'll use x squared here. So we have x squared because we're familiar with x squared at 2, for instance. So, let's see, how do I want to say this? I want to find the area under a curve, because we really see this with integration, right? So let's do it this way. Let's just do f of x, the height, with the width. Okay? And if we were underneath square root function, it looks like I drew something like the square root function. And let's do 4 again. So that would be 2. And this dx might be 0.01. I mean, that's going to get us a lot of decimal place accuracy. And that's one layer of change. The next layer of change might become 2.01 for a height. Well, that's not going to be the height, because I'm going to go over 1. So instead of being at 2, instead of being at 4, instead of being at 4, I'm going to go to 4.00401. Now, why did I do that? Because if you square 2, you get 4. But if you square 2.001, you get 4.00401. So maybe that's where I'm at. Maybe I'm going over here just a little bit. I don't like what I'm saying right now. All right? But I'm trying to say that this is capturing a little bit of area. And then as I move to the right just a little bit, there's another little bit of area. And these are really rectangles with a height and a width. And we're adding up an infinite number of those height times widths from A to B, from left to right, from A to B. Highlight area under a function with a single layer of a rectangular area, and we add it up. And when we do that, we get a new function. And that new function is a representation of the area accumulating under curves. Okay. Yeah, a little tired here. All right, but hopefully you got some practice, and this is for folks who maybe can't get in the classroom, but still want to learn and go up the ladder in this discipline. Well, I'm hoping that this might help. All right, ciao.